Okay, so welcome to the 41st video in the discrete structure series, and we are continuing our chapter of counting and discrete probability. In this chapter, we have already finished looking at basic counting principles, permutations, and combinations. We will resume the discussion of permutations and combinations again in the next video under the topic of generalized permutations and combinations. But before we do that, there is a topic of binomial coefficients and identities, and this will be the topic of discussion for this video. So we'll be looking at the concept of binomial expansion and the binomial theorem. And following that discussion, we're going to look at a couple of problems under the binomial theorem. And we'll be looking into one last topic today, and that will be the Pascal's identity and triangle. Here, we'll mention the Pascal's identity without proof. We'll see how it's useful to build something called a Pascal's triangle, and also solve a problem of binomial expansion that makes use of the Pascal's triangle. And with our goals set, let's get started with the first section of the video, binomial expansion and binomial theorem. First, let's build a couple of ideas about what a binomial expansion is. So if I have a sum of two things, x and y, this is typically called a binomial expression. And for the general case, x and y could be anything. They could be constants, they could be variables, or they could be product of variables and constants. So something like 3x square y plus z square would also count as a binomial expression. And when we talk about expansion, we mean the expansion on the different powers of this binomial expression. And we are already familiar to this with some extent. We know the formula for x plus y whole squared, and the formula is really a binomial expansion. This is equal to x squared plus 2xy plus y squared. I think we know one more by heart. I'll list it here. We know x plus y whole cubed. This is equal to x cubed plus 3x squared y plus 3 times xy squared plus y cubed. So a binomial expansion is just the expansion of any integer power of a binomial expression. And the generalization for these expansions for all the values of n is provided by the binomial theorem. So if I were to take my binomial expression x plus y and then raise it to the power of n, the result of this expression would be given by the binomial theorem. So next we want to provide a formal statement to the binomial theorem. But let us observe some patterns in these two expressions so that we have a better idea later of what the theorem actually means. So let's get started by looking into this simple expression. If I have x plus y squared, that is really just the product of x plus y 2 times. Okay, x plus y times x plus y. And our goal is to relate this expression to this expansion without actually multiplying. And to do that, the first thing that we want to figure out is what different terms will end up in my final expression. We know that when we multiply and expand this expression, this first x gets multiplied with this term and this term, and then the second term y again gets multiplied with this and this term. So my very first observation, all combinations of x and y of the order n appear in the expansion. So the order in this particular example is equal to 2 because I'm taking the square of x and y. And by my first observation, I can tell that all combinations of x and y of order 2 will appear in my expansion. So my term could be built with only x. In that case, the order has to be 2, so this term has to be x squared. And that is obtained by multiplying this x with this x. Now if I consider terms that consist both x and y, and if you see the order of this expression, the order is already 2 because x power 1 and y power 1. So 1 and 1 give me the second order. So this is going to be one term in my expression. And similarly, if I take only y, I'm going to get y squared. I promise it will be even more clear when we look at the example for the third power expansion. But for now, we want to be convinced that this expression, when expanded, will consist only these three terms, x squared, xy, and y squared. And the next question that we want to ask is what coefficients we want to put in front of these expressions. So I know from my result that I'm going to need 1 x squared, 2xy, and then 1 of y squared. But how do I figure out the coefficients 1, 2, and 1? So let's come back to this expression again. So here's the thought process. In order to get x squared, I must choose x from this expression and x from this expression. If that multiplies, I get x squared. And there's only one way to do that. I must choose x here and I must choose x here. So that means out of two sets, out of two expressions, I must choose x from both of them. Okay, so there are two terms, x plus y and x plus y, and I want to choose x in both of them. Moreover, the order in which I choose the x does not matter. If I choose this x first and this x first, the product will be x squared. But if I choose this x first and this second, the product will still be x squared. So I want to choose two x's from two expressions, and that should be a combination because the order doesn't matter. So this coefficient 1 is really the combination of 2, 2. Okay, from two expressions, choose two x's. And we know that the value of C2, 2 is equal to 1. And if we think similarly for the term xy, there are two ways for me to do this. I could either select x from here and y from here, and that would produce one instance of xy. But I could also obtain xy by choosing this x and this y. Therefore, in order to get the term x and y, I need to choose exactly one x out of these two expressions. So that means out of two expressions, I want to select one and exactly one to be x. And it's very important to understand that this selection of x fixes the selection of y. When I say that I select exactly one out of these two, then from the remaining order, I will be selecting y. And that comes because of the fact that the order of all of these expressions is same that we talked about earlier. Since this is x squared, this is second order. Since this is x1, y1, this is second order. So when I choose only one x, the other y is automatically decided by the order. So the term C2, 1 representing the one choice of x from either of these two expressions is equal to the number of terms xy in the product. And in order to get the term y squared, we can say a similar argument. We have no choice but to select y from both of these terms. But we are defining our combination in terms of x. So we'll say out of two x's, 0 of them will be selected. So if I do not select a x from both of these terms, I'm forced to select the y in both of the terms. And that will consequently make my term equal to y squared. And there's only one way to do that. C2, 0 is also equal to 1. So let us try to replicate this analysis for this expression for the third power. I'll just make up a little space. Okay, so this time I'm looking at the expansion of x plus y whole cubed. So that will mean x plus y will occur 3 times. And in this case, what different expressions will be a part of my result? So this time I know each term in my result will be of the order 3. Okay, this is of the order 3. 2 plus 1, this is also 3, 1 plus 2 is also 3, and y cube also gives an order of 3. But I also know that my term can either contain x, only y, or a combination of both x and y. The first thing that I want to do, as you know, is to ensure that the order of all of these expressions is 3. So I'll do that by considering x cube, because this is a term containing only x, so it must be 3 in order to reach the order of 3. The same thing will happen for y. This will be y cubed for reaching the third order. Now for xy, how many ways are there to reach the third order? See, I could have x power 1 and y squared. This would give me the third order. And I could also have x squared and y power 1. That would also mean the third order. 2 plus 1 is equal to 3. So by doing this, I can tell exactly which terms appear in my expansion. And the next thing I want to do is to figure out these coefficients. Following a similar reasoning process, in order to reach x cubed from each of these 3 terms, I'm forced to select x. So I really need to select from all 3 expressions, 3 x's. And let me change the position of these 2 terms because it makes more sense that way. Because I want these expressions in some order, you can see that the power of x is decreasing from 3 to 2 to 1, and here's no x, it is x power 0. So considering x square y as my term, so it's easy to guess, out of all of these 3 expressions, exactly 2 of them must be chosen to be a x. So this will be given by C 3, 2. Similarly, for this expression, exactly one of 3 should be a x, C3, 1, and in this case, 0 of them should be a x, and all of those others will be a y. So this will just be equal to C3, 0. I hope this explanation is clear because we'll use the same reasoning in order to derive the binomial expansion for any power n. But before we do that, there's one more observation to make. We argued that in order to reach x cubed, I needed to select 3x from 3 positions, from all of these 3 positions. But if I argue that in order to get x cubed, I have to select 0y from all of these 3 positions. So I'm simply shifting my focus from talking about x to talking about y now. So it is also true to say that in order to get x cubed, I can take the combination of all 3 terms and this time consider 0 y's. Okay, this 0 refers to a y. And this should also be correct. Arguing similarly for this term, instead of saying I want 2 x's, I could say I want 1 y. Okay, so this could be C3, 1. This could be C3, 2, and this could be C3, 3, meaning select all y's out of the 3 possible y's. So this means that once you have your expression, You want the biggest power to be the first term of the combination. So this 3 power goes to the first term of the combination, and that will always be true. But for the second term, you are free to start with 0 and head up all the way up to n, or you are also free to start with n, the highest value, and head down all the way to 0. Both of them will give the same expression and a valid expression. And to support my claim even more, we know this expression Cn, r is equal to Cn n minus r. We looked at this in yesterday's discussion. So this means that if I plug 3 here, and let's say a 1 here, this is the same as plugging 3 and 3 minus 1, that is 2. Okay, and that is why this 3, 1 and 3, 2 give the same value. Here we can observe the same thing, C32 and C31. We know that they should give the same value. And finally, if I were to consider r as 0, 3, 0 would be same as 3, 3 minus 0, and that would also be equal to 3. So 3, 0 is same as 3, 3. You can see 3, 0 is the same as 3, 3. You can also see the same fact here. So summarizing for the last time, in order to expand, you want to start with the highest power of some variable and reduce its power all the way to 0. So we started from x cube, went to x squared, x power 1, x power 0. At the same time, the other variable will start from 0 and go to maximum. So when I have x cube, I have y power 0, no y here. Here I have exactly 1 y, 2 y's, and then 3 y's. And once you have all of your expressions listed this way, you can start working out the coefficients. Every coefficient will be a combination of the highest power and something else. And that something can start from 0, go all the way to the maximum of 3, or it can start from 3, go all the way down to 0. And both of that will give the valid expression for the required power. So let's write this formally now. I think we're ready. So I'll say statement for the binomial theorem. So we want to calculate x plus y raised to the power n. And just from our discussion from earlier, we know this is equal to x power n. That will be my first term. My last term will be equal to y power n. And now we know the pattern. What will the second term be? So from the example, we know that the power of x in the next term will decrease by 1 and the power of y will increase by 1. So I have x power n minus 1 and then a y. Because I had y power 0 here, I'll have exactly 1 y or y power 1 here. And then these types of terms will continue. What will be the second last term? Let's do one before this. See, in the last term, there is no x. So in the second last term, I'll have exactly 1 x. And in the last term, I have n y's. That means I'll have n minus 1 y's here. Plus, and this is my last term. And now we want to work out the coefficients. We know that to calculate x power n, we want to take a combination of n items. And for the second term, I could either say all n of them should be x, or I could say 0 of them should be y. And we know both of that will work in the formal definition, and for convenience, we start with 0. So we'll just mention n choose 0 here. So writing n0 in this format is same as Cn, 0. And for our purposes, it means for all of the terms x plus y in this expression, choose 0 y's. Okay, that will give all x's. Now for the second term, I need to choose exactly 1 y and remaining will automatically be x's. So this will just be n 1. And eventually I'll reach this term where I need exactly n minus 1 y's. Out of n, I need n minus 1 of them to be y's. And the coefficient for the final term, y power n, as you would have guessed, is just going to be n. From all the terms x plus y in this expression, choose y in all n of them. So this statement is called the binomial theorem. And there is also a condensed way to write this in terms of summations. So I can say this is a sum and I'll iterate over this value. It goes from 0 all the way up to n. So I'll just say j is equals to 0 to n. And what do I have in each of these terms? Each of these terms starts with a combination. I'll list the combination here. The first term in the combination is always n. So this will always be n. And the second term over here will just be equal to the value of j. For this term it is 0. For this term it is 1. So whatever the value of j is here, the same value will be here. And now I know in each term there is going to be some power of x and some power of y. And that pattern is also easy to see. For 0 here I have n minus 0. For 1 here I have n minus 1. So whatever I have here, I have n minus that quantity here. You could also verify it here. I have n minus 1 quantities here. And if I take n minus 1, this will just be equal to 1. And it works out. I have a power of 1 for x here. So whatever value I have here, n minus that value is the power of x. The same thing works for the last term as well. I have n here. Therefore, n minus n is equals to 0 is the power of x over here. Therefore, when I have any j, n minus j is going to be the power of x. The power of x is going to be equal to n minus j. And what about the power of y? See, the power of y in the first expression is equal to y power 0. And that is equal to the j. For the second expression, it is y power 1, which is equal to the value of j in here. And that works for all the expressions. If you look at this one, y power n minus 1, and the value of j is also n minus 1. Y power n, and the value of j is also n. Therefore, the power of y for any given term will just be equal to the value of j. And this one is the condensed formula for the binomial expansion. So this is an extremely useful result. Alright, now we're ready to tackle some problems. Let me put one question here. And as always, starting with the simplest ones. This one asks, what is the expansion of x plus y raised to the power 4? So we can directly apply the binomial theorem for this. I know that x plus y raised to the 4th power is equal to the summation of sum j from 0 to 4 containing terms composed by x, y, where the power of x starts from 4 and decreases by j each time, and the power of y starts from 0 and increases by j each time. So this is just equal to j. And I have a combination term here, and this will just be equal to 4 choose j. Now I can expand this. This is going to give me x power 4 with the coefficient of 4 choose 0. And there's going to be another term where x decreases by 1, x cube y. The coefficient will be 4, 1. Plus, the next term is going to be x squared, y squared, decreasing 1 from the power of x and adding 1 to the power of y. And this coefficient is going to be 4 choose 2. And continuing with the same logic, the next term will contain x, y cubed, and the coefficient will be 4, 3. And for the final term, the power of x will be 0 and only y power 4 will remain. The coefficient will be 4, 4. And now we can simply write this as x power 4, 4 choose 0 is 1. And then you can calculate all of these values. So this will give me 4 x cubed y, 4 choose 2 is 6, plus 6 x squared y squared. And if you want to be fancy, you know that 4, 3 is the same as 4, 1. So once you reach the middle term of your expression, all the coefficients will start to repeat in the decreasing order. So the next coefficient will also be 4, and the next coefficient after that will be 1. I want 4, 4, and I know that is the same as 4, 0. So this will just be 1 times y raised to the power 4 or y raised to the power 4. So pretty simple question, applying the binomial theorem directly in order to reach this expression. Next we'll look at a more common and arguably more important type of a problem. Find the coefficient of x power 12, y power 13 in the expansion of, and we are given two expressions. One says x plus y raised to the power 25, and the second one says 2x minus 3y raised to the power 25. Alright, so what is the question asking? I want the coefficient or the number that appears before this term, x power 12, y power 13. I see that the sum of 13 and 12 is 25, and 25 is the power that I'm looking for. Therefore, x power 12, y power 13 is a valid term that will appear in these expansions. And these examples really demonstrate the power of the binomial theorem, because it would be really hard to actually expand this and to look into the coefficient of this term. The expansion of this expression will contain 26 different terms. For any n, the number of terms in the expansion will always be n plus 1. And even those 26 terms will come from a lot of arrangement, addition and manipulation. But thanks to the binomial theorem, we can compute this easily. We know that x plus y raised to the power 25 is given by this expression. It's going to be the sum of any j from 0 to 25. And you see 0 to 25, that gives me my 26 terms. That's how I'm able to tell. And I know this will involve a combination of 25 things chosen j at a time. And we'll start with the highest power of x and decrease by j. And for y, we'll start from 0 and increase by j. Now I know that my desired term contains x power 12. So this implies this power of x, 25 minus j, must be equal to 12. And this gives me j equals to 13. And you should be able to see, I can also find that j is equals to 13 by looking at y. The power of y is 13 over here, and the power of y is just j over here. So I can say j is equal to 13. And that should give you another hint why any random x and y power will not work. The powers must add to the power that you are looking for, so that the order of the expression is maintained. So 25 must be the sum of 13 and 12. And because of that, the value of j is same whether I look at x or y. It doesn't matter. But once I figure out j is equals to 13, I know that the coefficient of this term is just going to be the number that appears before it. So it's just going to be 25 choose 13. And this value is just a very large number. I'll mention this for completion, 5200300. So this is going to be the coefficient of this term in this expression. And now we are ready to tackle this problem. It is slightly different and we'll be using a few tricks, but the core idea is still the same. The first thing that you want to do is to retranspose this. We know that this is equal to 2x plus minus 3y. And I can raise that to the power of 25. The reason that I want to do that is because I need x plus y in my expansion and not x minus y. So this 2x, the whole term, plays the role of my x, and the whole term minus 3y plays the role of my y. And now by looking at this expression, I can write the binomial expansion. I know that 2x plus minus 3y whole raised to the power 25. And this will be equal to the sum of sum j from 0 to 25. So I'll have my combination here. 25 choose j. The power of 2x will decrease from maximum. 25 minus j. And the power of the second term minus 3y will increase. Minus 3y raised to the power of j. And let's do one more rearrangement here, trying to isolate the coefficient and leave x and y alone. So it's just a rearrangement. Let me write the same thing. J is equals to 0 to 25. And if I look at all the constant terms, that will form my coefficient. So I'll have 25 j, and 2 raised to the power 25 minus j will also be here. And minus 3 raised to the power j will also be here. And all of this thing will serve as my coefficient. And apart from this, I have my x's and y's. X is 25 minus j, and the power of y is just j. And you can see from this point onwards, the problem is kind of the same. We compare 25 minus j with this 12, or we can simply compare j with 13. Either way, it's the same. And so with a similar argument, we'll figure out that j is again equal to 13. And similarly, if I try to evaluate what the coefficient is, it's going to be 25 choose 13 from this expression. And then I have 2 raised to the power 25 minus j. That will give me 2 raised to the power 12. And then I have minus 3 raised to the power 13. And for this answer, we'll just leave the coefficient here, because I cannot imagine that this number would fit in my board. Alright, next we'll be looking at a couple of corollaries in the binomial theorem. And this can be asked as individual proof questions. So I'll just mention this as a question. Prove that the sum from k is equals to 0 to n of the combinations n comma k is just going to be equal to 2 raised to the power n. So we can prove this as a direct result from our binomial theorem. We know from our statement of the binomial theorem that x plus y raised to the power n is equal to the sum of sum k from 0 to n. And this time I'm using a k instead of j because I want k in my expression. Not a big deal at all. But the idea is I have my terms n k here, and then actually start from the maximum n and decrease by k, and while start at 0 and increase by 1 each time. So this already looks a lot like this. And now all we need to do to reach this expression is to make a few substitutions. I know that I need 2 power n, and I can get a 2 on the left hand side in many different ways. So I could choose x as 2 and y as 0, and this will be 2 raised to the power n. But if I make this choice of 2 and 0, I see I'm getting 2 raised to the power something over here. And this term will be 0 raised to the power of k. Is that the direction that I want to go to? I really do not, because what I want is for the multiplicand of all of these terms to just be a 1. See, nothing should be multiplied with this term. And I can ensure that by choosing x as 1 and y as 1, because 1 power anything will just be equal to 1. And it also works for my left hand side. 1 plus 1 will just give me 2. So substituting x is equals to y is equals to 1, we can simply say that 1 plus 1 raised to the power n. And this will be equal to sum of k is equals to 0 to n. This doesn't change. The combination n k doesn't change. And what happens here? I have 1 raised to the power n minus k, and then 1 raised to the power k. Both of these things are just 1. And what follows from this is my result. So I'll write this on the left. Summation k is equals to 0 to n. And choose k is just going to be equal to 2 raised to the power n. So this is one proof for this expression which comes from the binomial theorem. And there's another way to prove this. If the question says prove this by counting subsets, we can provide this proof. So let me show you with an example. I want to consider a set S with 3 elements. In fact, the number of elements that I want to assume should be equal to n. But for this demonstration, I'll just choose 3 elements, A, B, and C. Now I know that the number 2 power n represents the number of subsets. So for this set containing 3 elements, there will be 2 raised to the power 3 is equals to 8 subsets. Okay, so I want to view 2 power n as the number of subsets of a set containing n elements. And I want to complete my proof by showing that this left hand side is also counting the same number of subsets. Just to make sense of that, let me write this expression in context of 3 elements. This is going to transpose to the sum of k is equals to 0 to 3. 3 choose k. And if I expand on this, I'll get a 3 choose 0 plus 3 choose 1 plus 3 choose 2 plus 3 choose 3. And now look at this. What does this mean? This means from my 3 elements A, B and C from this set, choose exactly 0. Okay, so if I choose exactly 0 from this set, what am I going to get? I'm going to get nothing, and that's going to give me my empty set. This is one of the subsets that I counted in 2 power n. Now according to this term, I need to select exactly 1 out of 3 elements here. So that will give me 3 possible subsets. One subset will contain only A, one subset will contain only B, and the third subset will contain only C. So these 3 subsets are being counted by this term. In fact, all subsets of exactly 1 element are being counted by this term. This term is counting all subsets with exactly 2 elements. And finally, this last term is considering subsets with 3 elements. So from 3, I need to select all 3. So that will give me the subset containing all elements A, B, and C. So it turns out that by starting at the first term and ending on the last one, I can account for each of the subsets counted by 2 power n. Because all of the possible subsets are exactly counted by this expression. And so that is another way to prove that this expression is equal to 2 raised to the power n. So let's formalize this a little bit. So we can start by saying the right hand side 2 power n counts all the subsets from a set of n elements. Also from a set of n elements, n0 subsets contain exactly 0 element, n1 contains exactly 1 element, and if we continue on this thought, the final term nn, these many subsets contain exactly n elements. And we can continue on this. Therefore, all subsets are counted by simply the sum of all of these terms, right? So n0 plus n1, and then it goes on all the way up to nn. And I can write this in the summation notation. From k is equals to 0 to n, I have n and then k over here. So this is another proof for the same expression. I can reach this expression by also considering the law of subsets. Alright, now moving on to the next question. We need to show that the sum of 0 to n, and this time I have minus 1 raised to the power k. And I have the combination nk, and I want to show that this is equal to 0. So I think just a hint will be enough for you guys. We again start with the binomial expansion for x plus y. I know x plus y raised to the power n. And this time the substitution that you want to make should be pretty easy. If I select x as 1 and y as minus 1, and there is another possibility, I could choose x as minus 1 and y as 1. Both of these will result here into a 0. But you should also be able to see that I want minus 1 raised to the power k here. And the power of k here is tied to y. So if I select y as minus 1, I get minus 1 to the power k. But if I select x as minus 1, I get minus 1 raised to the power n minus k. That is not very helpful. So in this case, we'll start by assuming x is equals to 1 and y is equals to minus 1. And if you just substitute those values, on the left hand side you get 0 raised to the power n, which is just equal to 0. And on the right hand side, I still have this summation from 0 to n. This term nk doesn't change, independent of x and y. X I'm simply plugging as 1. So 1 raised to the power anything will vanish out. It will just be a product times 1. And that will leave me with y raised to the power k. And in my substitution, I have y is equals to minus 1. That will give me minus 1 raised to the power k. So I did not do this formally, but this should be really simple. Exactly the same thing that we did in our last problem. And if you are wondering, there is no set related proof for this problem. So this is the way that we are going to solve this. Alright, we'll move on to the last topic of the day, and that is Pascal's identity and triangle. So let us first look into Pascal's identity. And this identity states that the combination of n plus 1 things taken k at a time is equal to the sum of combinations. First by taking k minus 1 out of n objects, and second by taking k out of n objects. And this pattern is easier to observe in numbers. So also what this means, so if I take 5 for example for any of my n, and I could choose any number less than 5 over here. So let me say 3, and I want to add this with the same combination 5 but 1 more than 3, okay, 4. And according to this rule, this will be equal to 6, 4. Similarly, if I start with 3, you start with 1, and let's say 3, 2, this is going to be equal to 4, 2. So for any n like 3, if I choose a value of k and add it to the same combination with the value of k reduced by 1. So from 2 I have 1, then this will give me the combination by increasing n by 1 while retaining the same k. And this identity is really useful, and I promise it will make more sense later, to construct something called a Pascal's triangle. So a Pascal's triangle is simply a triangle formed by taking the binomial coefficients. So let me show you how this triangle is formed. The top of my triangle is just 0, 0. Okay, this is my first node. And every time I write something like this, you should consider that the top term is going to be the power that I'm looking for. So if I'm doing x plus y raised to the power 0, I'm going to get only one term, that is going to be 1, and that 1 is being represented by this 0, 0. Similarly, if I take x plus y raised to the power of 1, it is just going to be x plus y. And this is like saying 1 times x plus 1 times y. So the next layer in my Pascal's triangle will show the different coefficients when the power is 1. Okay, and the two coefficients are going to be 1, 0 and 1, 1. We know this from the binomial theorem. Similarly, if you consider x plus y whole squared, this will give me x squared plus 2xy plus y squared. So these three terms, 1, 2 and 1, relate to the second power of my binomial expansion. So that will add one more layer in my Pascal's triangle. So the first term will be 2, 0, the second term will be 2, 1, and the third term would be 2, 2. And let me do one more layer to clarify the point. If I'm taking the third power, my coefficients will be given by 3, 0, 3, 1, 3, 2, and then 3, 3. Now you should be able to imagine that I can keep building this triangle for any power that I want by adding more layers. So the first layer is going to be for the 0th power. As you can see from this 0, the second layer is going to be for the first power. You can see both of these top powers are 1. The third layer is going to be for the second power. All of these are 2. All of these are 3, and so on. But what is the advantage of drawing this triangle? And to show you what I mean, let's first consider everything on the outside of this tree. Okay, so this term, this term, this term, this term, we'll consider them to be outside, and we'll also consider all of these terms to be outside. Okay, this will be outside, this will be outside, and this will be outside. But what about this term 3, 2? This lies on the inside. So I hope you are able to see that this lies on the inside, this lies on the inside, but this one lies on the outside because it is the first term on the outside of my tree. So if I look at all of these outside terms, so if I look at 0, 0, 1, 0, 2, 0, 3, 0, in each of these terms, I'm just selecting 0 out of anything. Okay, 0 out of 3, 0 out of 2, 0 out of 1, and 0 out of 0. So all of these values are simply going to be equal to 1. There's only one way to select 0 out of anything. And that way is to not select anything. So we still say that there is one way to select nothing. And if you look at the right edge of this triangle, you'll find items like 0, 0, 1, 1, 2, 2, 3, 3. So for all of the terms on the right edge, for a given n, we are selecting all of them. And again, there is only one way to select everything, right? If you want to select 2 from 2, there's only one way to do that. If you want to select 3 from 3, there's only one way to do that. So also for the right edge, all of these terms will be equal to a 1. So I can see that it is really easy to calculate terms on the outside. They are just equal to 1. But what about these terms on the inside? And that is where this Pascal's identity is so useful. And if I get back to the pattern again, if I have 3, 1, and the same 3 with 1 increased, right? 3, 2. If I add these two, it will be equal to 4, 2. So the value in the power will increase by 1, and the value in the choice will be the greater one, right? 1 and 2, 2 is greater, so that will come over here. And because of that rule, let me consider this inside element 2, 1. I can say this will be the sum of this and this. You can see I have 1, 0. This is like 3, 1. And I have the same one over here, but this 0 has increased to a 1. And if I add these two terms, I'm going to get a 2 over here. And on the bottom, it's going to be whichever is greater from this 0 and this 1. So 1 is greater. So this will be here. So you don't have to remember this. You can simply add when you are creating the triangle. But I'm explaining you why this triangle works. If you now look at this inside term, 3, 2, I can say this is the sum of this and this. Why? Because this has 2, 1 and this has 2, 2. So if I add them, the 2 will convert into a 3 and the larger of 1 and 2 will be chosen. So this means that all of the terms in the outside are 1 and all of the terms in the inside can be computed from the previous layer by using Pascal's identity. So in order to draw this entire triangle, I do not have to compute any combinations. And that is the big idea behind the Pascal's triangle. So let's draw this actual triangle with real values this time. So I start with a 1 and this corresponds to the power of 0. And now in order to calculate a layer for the power n is equals to 1, I can simply branch this into 2. And since these are edge cases, I'll simply say these are equal to 1. Because up to this step, this one is on the outside and this one is also on the outside. So this will be a base case. I can directly tell everything on the outside is just 1. So the second layer is just complete. If I want the layer for n is equals to 2, I'll do exactly the same thing. First expand on the outside. I have 1 over here. Expanding on the outside. I have 1 over here. And now I use Pascal's identity. The sum of 1 and 1, 2 will go over here. And the reason this 2 is equal to the sum of 1 and 1 is because what we discussed earlier, is because of the Pascal's identity. And let me draw one more layer. So I'll start by expanding this 1 and this 1. The outside is done. For the inside, I add 1 plus 2, that gives me 3. I add 2 plus 1, that also gives me 3. And you can see by doing this, I can reach any power I want. This is for n is equals to 3. And I can continue for 4, 5 and 6. So the Pascal's triangle helps us to calculate all of the binomial coefficients recursively. And I can use this triangle to directly write a binomial expression. So if I want x plus y squared, I know that I need to consider this layer with 1, 2 and 1 because that stands for the power of 2 that I want here. And I know that the terms in this expression, it starts with the highest power of x and then it will reduce by 1 giving xy. And in the next term, there will be no x, simply y squared. And what coefficients should I put in these places? I can borrow the coefficient from the Pascal's triangle. It says 1, 2 and 1. So I can say 1, 2 and 1. And therefore x plus y whole squared is equals to x squared plus 2xy plus y squared. Similarly, x plus y whole cubed is x cubed plus 3 times x squared y plus 3 times xy squared plus y cubed. Alright, let's conclude our video with one final example. Draw the Pascal's triangle for n is equals to 4 and use it to find the binomial expansion of, let's say, a plus b raised to the power 4. So we have already done this in the example, just formalizing it here. We'll say solution, drawing Pascal's triangle for n is equals to 4. And I'll draw the triangle quickly here. So this is for n is equals to 0, for n is equals to 1, n is equals to 2, 3 and 4. So next we say, we know that the terms in the expansion are considering decreasing powers of a. So what are the terms? We'll just list them using commas first. So I know the term is going to be a power 4 first, a cubed b, and then a squared b squared, a b cubed, and b raised to the power 4. Now borrowing the coefficients from the Pascal's triangle, we are able to say that a plus b raised to the power 4 is just the sum of all of these terms with their corresponding coefficients. So this will be equal to a raised to the power 4 plus 4a cubed b plus 6a squared b squared plus, I can take this 4 again, 4ab cubed plus b raised to the power 4. So I hope this problem is clear and the idea about the Pascal's triangle is also clear. Now we did not cover the proof for Pascal's triangle in this course because I think we don't need it. But if you are interested or do need it by any chance, it also uses the same proof technique that involves counting subsets. So my plan at the end of this course is to make 2 or 3 extra videos covering all of the topics that I've missed and the topics that you guys are interested in learning. So if you can point out anything that has been missed or if you have any questions at all, please feel free to ask in the comments. And with this discussion, we complete our topic of binomial expansion and Pascal's triangles. From the next video, we'll be starting the topic of generalized permutation and combination. And under that topic, we'll discuss all of the special cases in permutations and combinations like undistinguishable objects, repeated objects, circular permutation, and all that type of stuff. So that is all for today. I'll see you guys in the next one. Have a good day and bye.